Hello, everyone, and welcome to the first Google Lunar X Prize Team Hangout. My name is Dr. Pamela Gay. I am the principal investigator for CosmoQuest, a project that is very Earth-based, but we're down here mapping the moon in hopes that someday people will go and explore it, and these are some of the people that are working to make that exploration possible. Today I have with me John Thornton, who is the Chief Executive Officer over at Astrobotic, which sadly sometimes gets written as Astrobiotic, which I'm sure must be an interesting trial for him, but it's Astrobotic, astronomy, robotic combined together. I also have with me PhD student and electronics guy, Karsten Becker, and the CEO, team lead of part-time scientists, Robert Bohm. Today we are going to have each of these two teams overview what their mission plan is at this point. They are two of the 18 teams still actively pursuing the Google Lunar X Prize. The Google Lunar X Prize is put out to help encourage people to build rovers or some other form of robotic critter that will go to the moon, go a distance of 500 meters, and then send back video to Earth. And there aren't any restrictions on how you go those 500 meters. In my head, I've always envisioned like a little Sony robot kind of doing the boogie as it goes the 500 meters, because that would be great for YouTube. But they have much more scientifically planned ideas of how to do this, and they're going to introduce us to their plans. And John, I'm going to go ahead and start with you because you appear furthest to the left on my screen.
Awesome. Thanks, Pamela. Thanks for having me today. It's really great to talk about what we're up to. So our first mission wins the X Prize and flies to a place called Locus Mortis on the surface of the moon. So this is it translates to Lake of Death, which sounds dramatic, but the reason that we go there is there's a very unique feature that only exists there on the moon. It's called a skylight. It's 100 meters across and 100 meters deep, and if you can get to the bottom of it, it's an entryway to a lunar cave network underneath the surface. They've found upwards of 150 of these on the surface, but the one that we like at Locus Mortis has a ramp that you can actually get down into and potentially get down and explore these pits. So our first mission goes there. What we do as a business and as a company is we sell payload. So we're like a UPS or FedEx to the moon. So we'll be bringing many other payloads from around the world with us on this first adventure. We'll also have a rover on board that will drive 500 meters, and it's very likely that we'll have other X Prize teams along board with us. So it will be an incredibly exciting adventure, and that's just a quick snapshot of where we are.
So Robert, would you like to introduce us to part-time scientists?
Okay, hello everyone. I'm Robert from the Part-Time Scientist, and as a little bit like an elevator pitch, what could be said about our team is that we're a private team of scientists and engineers, so working part-time on this mission to the moon, so really a technology enthusiasts. And our goal is actually to establish a foundation of technology to support ongoing private exploration of the moon. Because for us, I think it's not so. The focus is not on having one mission going to the moon or like being a delivery service to the moon, but actually establishing a layer of technology that makes it possible for everyone to access resources in space a whole lot easier. So if you think about space exploration, then everything sounds like things sound like they're settled. So it's like, oh yeah, we have communications, but in reality, things are a little bit more complicated. And our goal is to offer some solutions which hopefully solve currently existing problems a little bit better. So it was a little bit overly complex definition of what we do, sorry. So yeah, and together here with me is Carsten from our electronics team, and yeah, maybe Carsten, do you want to say something?
Hi, yeah, I'm Carsten from the electronics team, and so I'm concerned with getting the electronics to the moon, and one of the things that I noticed is that especially in the space industry, that electronics are very expensive, and so we want to see what technology, and especially they are very outdated. So if you take a look at Curiosity, it is a processor that is as old, that you wouldn't even put it on a current smartphone, But so we want to check what current technology we want to use and see what we can do with it on the moon. Hopefully, drive around and take pictures. That would be great.
Yeah. So to say it as I said already, our team is all about technology and finding new ways to put new technology to solve existing problems that we have in space. So yeah, of course, our goal is also to send multiple missions to the moon, but the very first one is just as a technology demonstration. So we try to cramp up as much as interesting pieces of scientific experiments or new technologies into this mission and try to see how it performs and what value it adds to future missions.
Now, one of the great things about the Google Lunar X Prize is, while the primary goal is to go successfully land on the moon, successfully go 500 meters, successfully send back video, there are a variety of other milestone and additional challenges that range from technology challenges to Apollo heritage challenges, and each of your teams is striving toward different of these additional goals. John, can you tell me which of these different goals your team is working toward?
Sure. Our team's going after the distance prize, which is driving 5 kilometers. So the way that we'll do that when we land next to this pit is we'll land next to the pit, we'll drive up to the rim, and we'll explore that pit and drive all the way around it and look into it for the very first time from the surface. We've only ever seen these pits from space, so it will be incredibly exciting to actually see these up close and see how these things were formed. No one knows how they were formed, which is incredibly exciting. And it's also really exciting to scout out the location because these pits, especially this one destination, has a ramp on it, which means that it's a potential site for future humans to habitate. So if you think about it, if you're underground on the surface of the moon, it's the same reason that you would settle in a cave here on Earth first. It protects you from the elements. If you're underground, you're protected from the solar radiation, which currently limits the careers of astronauts, because once you hit your dosage rate, you have to come home. But if you're underground on the moon, you're protected from that. It also can protect you from micrometeorites. The moon doesn't have an atmosphere like we do here on Earth, and those can come flying in and become a problem for people. And if you're underground, you're also protected from the thermal extremes that exist on the surface. It gets up to 120 degrees Celsius, which is about 250 Fahrenheit, down to liquid nitrogen cold, which is about a minus 180 degrees Celsius. So if you're underground, you're protected from all of this. So our first mission is going to spend a lot of time exploring that pit, and that's likely how we'll get up to about 5 kilometers of distance. The second prize that we're going to be going after is the surviving the night. So in order to survive the night, you have to operate after a cryogenic cold period of 14 Earth days. So it's minus 180 degrees Celsius for 14 days. It's incredibly cold. A lot of times governments solve this problem by using a radioisotope. So it's essentially a hot material that's decaying slowly over time, and you're able to use that heat to keep your spacecraft or rover warm over time. Because we're a commercial entity, we don't have access to that. We don't have the budget for that. It's incredibly expensive, and you eventually need a presidential approval and a lot of schedule to support it. So we're not going that route to survive the night. Our approach is to find electronics and find technology that can just survive that cold. So the very first thing that we've found so far is a battery that you can put down in liquid nitrogen temperatures and bring back up the next day, and it still has the same charge as it did before it went down. So we found a battery that can survive that night. So it's a really big step, and all the tests that we've seen so far are proving very successful, that the electronics can in fact come back the next day. So we're going after the distance to explore the pit, and we're going after surviving the night so that we can extend our stay on the moon.
And just to help provide our audience who may not be as familiar with batteries dying in the cold and radioisotopes, radioisotope is a fancy scientific word for a bunch of atoms that are not entirely stable and go through a radioactive decay process. So you have things like uranium, cesium, plutonium. There's a whole variety of different choices that you have. Some of them get used in medical research. Some of them get used to treat cancer, and they actually will put some of these into the human body. And when they decay, they release, among other things, heat. And with a spacecraft, that heat can be used to provide energy and to just keep the spacecraft warm. This is how the Cassini mission is working. The New Horizons mission, which is the fastest thing in the solar system, that's, well, fastest man-made thing off the planet in the solar system, is on its way to Pluto. But we're out, for the most part, in the United States, of the materials that we'd normally use, so even NASA folks are having trouble getting it. Batteries in general, just for a whole lot of chemical reasons, you get them cold, they stop working. This is why when you're hiking, you often have a headlamp with a battery pack that's up close to your body along with your water bottle, so your batteries don't freeze and your water doesn't freeze. Well, you don't have that body heat in space, usually. So we have to find new ways to solve old problems. But yeah, these are great challenges. Now, I know, Robert, your team is actually looking to go after a completely different set of different challenges. Can you tell us about the challenges that you're chasing?
Okay, so first of all, I will start off with the challenges that we have in common. So the basic GLXP challenges that we're going for are, of course, the Range Bonus Prize, the so-called Lunar Night Survival Prize, and the Apollo Heritage Prize. So to understand why we're going for these three distinct Google Lunar X Prize challenges, you have to look at where we're landing. So our goal is to land in the Taurus-Littow region, which is where Apollo 17 sat down. And this is you can't call it crater. It's more like it's like a very open valley, and it's a very good region from the surface area. So it's like, to more easily describe it, you could easily imagine it being a little bit like a beach with some rocks on it. So it has a very good low average rock distribution, which means there are not so many rocks lying around, which could be a problem for a rover. However, there's of course a lot of so-called lunar regolith, which is this fine gray powder that you have on the moon. And this actually is quite a little bit nasty stuff, but we can talk about in a few minutes. But to talk about again, the reason why we're going for Taurus-Littow is actually because we're interested in exploring a region, a very large region. So, so to understand, the goal is not to build a rover for us that can drive more than 5,000 meters. It's actually to build a system which can drive as much as it can. So exploring as much of the surface area as possible. So that is the reason why we're, for example, thinking about combining the system with, could call it artificial intelligence. So it's like it's autonomous autonomous control. Because the fastest way to actually have something explore the surface of the moon is not being a rover which is operated from Earth because of this 3-second delay, which makes things a lot complicated for the operator here on Earth, but it's actually to have the rover drive on its own. And with real-time autonomy, for example, in the system, it would be possible to drive as fast as possible for the rover in this case. And there's a design goal that for everything that we've built for our mission is to last to be up about 12 months from an Earth perspective. So, and this means that we're not designing things like, for example, you could actually design a mission that just fulfills the basic GLXP requirements, like, I don't know, building a rover which falls apart after 5,000 meters.
Planned obsolescence.
Yeah, actually, it would even be an interesting design, because I saw some people propose some designs, and let's say it's not so. I think it can even make sense to design something like this. But I think for what we are aiming to prove that a certain new technology is capable of doing something, for example, we're using a special type of brushless drives, which was originally intended to operate on the ISS, which even got tested partly on the ISS as part of the experiment. So it's things like these that we actually want to test drive and make available to future missions. So yeah, actually, it wouldn't make sense to design things to fall apart. So another thing that I found very interesting is the rules of the GLXP. The basic rules, something that fascinated me once I decided to found a team and join the competition was that the rules had some very strict requirements, for example, on image quality. So the GLXP guys were asking for very high image quality on the camera, and by that time they were proposing this, I think it was 2007, there was really no such camera available on the market which could deliver such image quality. And it was a very interesting challenge for our team to develop a camera which has a very low power consumption and provides the image quality that is even a little bit better than what is required and adds a scientific value to it. So actually it can show you much more things that you couldn't see with the normal human eye if you were on the moon. Carsten?
Also we're Germans, so we don't build cars that fall apart after 5 kilometers or something like this. But even if you're having radioisotopes or something like this, it's not very easy to survive the lunar night. It's just the jade rabbit from China was showing.
Yeah. No, this is a serious problem. So here on Earth, when we build houses and things like that run off of solar power, they generally have large battery packs and capacitor systems in somebody's garage or basement or backyard in a shed that are getting fully charged up by the solar energy that's being delivered from solar panels on the roof or in the backyard. And then during the night when the sun is down on cloudy days, the batteries are the sole source of power unless you also have backup off the grid. This is part of why so many houses that are built off the grid combine solar and wind power, because quite often the days that are cloudy have wind, and the days that are beautiful and clear may or may not have wind. But batteries can only last so long, and so what they've done on Mars and what missions that have survived the night on the moon have done is go into a sleep mode where they simply keep the spacecraft warm enough that hopefully its hopefully its computers keep going enough, keep it warm, but otherwise shut off all non-essential systems in hopes that those batteries will carry it through. It was originally hoped that Mars Phoenix would survive the winter when it was so bitterly cold, and down in the polar region it was getting just the smallest amount of sunlight every day. It didn't survive. Spirit and Opportunity both lasted a good long time. Opportunity is still going. Spirit died during its last winter because its solar panels, they weren't able to maneuver it to get sufficient light to keep it warm. Well, Mars winter, you're still getting sunlight. Lunar night, well, it's half a month long. So you're kind of stuck, and you have to keep yourself warm, keep your systems going, and you have to wake up on schedule at the end of all of that, and it's just not easy. Now, the Apollo Heritage Challenge is actually something that I found very interesting, and there's actually recently been a lot of discussions internationally on protecting these heritage sites. Is this something that you'd like to discuss at all, Robert?
Yeah, of course. So there has been proposed, I have to admit I don't have the numbers on the top of my head, but I think they have proposed a different set of safety keep-out radiuses, so zones where you don't have to enter with your, for example, rover, around an Apollo landing site. So, for example, we can't simply drive up to the flag of one of the Apollo missions and just do a close-up of it, because in this case we could actually drive over some of the footprints that the astronauts left. So there's a very distinct regulations, and we intend to stick to these. Yeah, and I don't know. I think it makes sense in this case, because actually protecting the heritage sites that are there. But the interesting thing for us is, for example, to get closer. The most interesting thing, actually, in this case, is getting closer to the. I hope the name is right. The Apollo. How was it called? The Apollo Lunar Rover. Not the rover. I think it was called something like Lunar Roving Vehicle.
Yes.
The
car with piano wire wheels.
Yeah, this one. Yeah, and actually this is what is really interesting for us, because it's based off a lot of different composite materials, and we want to study of how these materials decayed over the past 40 years on the surface of the moon. And this will be really interesting, because there is a long catalog of things that have been used as part of this car. And yeah, this is actually very interesting to understand what happened to it and how does it look like today.
One of the other questions that's very interesting about the Apollo sites is, for example, there are those mirrors, and those are starting to decrease in reflectivity. And so the question is why? Because on Earth it's quite obvious. If you put a mirror on the beach, there will be sand blown above it, but there is no wind on the moon. And so the question is, why did it stop reflecting like it did on the first day? And so this is another very interesting item, which is also why there's such high protective zones, because if you're flying over it, then they know why it stopped reflecting.
Yeah, this is where we go back to regolith, the fine white shiny part of the moon. When you look at the moon from the Earth, that's all fine powder. It's silicas. It's basically, think of the stuff on the whitest beach or the whitest dune you've ever seen. Make it even finer, make it even sharper. You don't want to be blasting that stuff up. And there's a lot of open questions. For instance, does the flag still have any color, or has the UV light from the sun blasted that free? Has the radiation from the sun, is it the photoelectric effect that's causing those mirrors to no longer reflect the way you'd like? How do the plastics, how do the metals, how do all of these things break down over time? We're working as a new generation of space explorers, and you are probably 2 generations beyond the people who last walked on the moon. And as you go forward, we're looking towards getting more people on the moon. And John, the cave system that you're potentially going to explore is one of the great discoveries that has been made just in the past 10 years, that there are these cave systems in the lava tubes on the moon. And I'm going to go ahead and pull up an image of your landing region if you could discuss this a little bit more with our audience, please.
Sure. The lava tubes are incredibly exciting. The same kinds of features occur here on Earth, but they're much smaller because of the gravity difference. So it's thought that the ones on the moon are potentially 10 times bigger than the ones here on Earth. So the ones here on Earth can be about 30 feet in diameter. It's thought that the tubes underneath the surface of the moon could be as large as 100 meters in diameter, or 100 yards across, which is incredibly exciting. I mean, you could imagine building an inflatable habitat inside of one of these caves. So as you can see in the image here, I mean, this is Lacus Mortis as it lies. There's actually 2 skylights in this flat area. This is the flat area surrounding that large crater in the center. And one of the skylights in particular is the one that we go to because it has one of the walls is collapsed and there's a ramp to get down underneath the ground. It's thought that the way these things were formed was that the moon was flowing with lava on the surface, and as that lava cooled from the outside first, and then there was a crust of solid rock, and then underneath you'd have lava flow still. And as that lava flowed out and emptied out, you were left a cavity or a cave. And it's thought that there's quite a few of these around the surface of the moon. What's really interesting is if we can figure out a way to explore these on the moon, there's also these same features exist on Mars. And there's many hundreds more actually on Mars for whatever reason. And it's possible that if you think about the deepest, darkest places that we find life here on Earth, way deep down in the ocean or way deep down into caves, it's possible that there could be life inside of one of these caves on Mars eventually. So if we could figure out how to get in and around these things on the moon, potentially create a base inside of it, and learn to live off the land of the moon and to learn to live off of Earth, it could be incredibly compelling to then extend that technology to a Mars expedition someday.
And you're now starting to sound very much like you're planning to recreate the moon as a harsh mistress with a little less of the revolution and war going on. What's truly awesome about these caves is we actually got extraordinarily lucky with the Apollo landings. Our sun periodically lets off giant blasts of coronal mass ejection, solar flares, all of these different events stream high energy particles. And high energy electrons is a fancy way of saying something that can blow your DNA apart toward the Earth. And here on the surface of the planet, we're protected by the Van Allen radiation belts, the Earth's magnetic fields, our atmosphere blocks out X-rays and the harshest ultraviolet light. We're safe. The astronauts in the International Space Station are moderately safe, but they still have to periodically seek refuge in one of the most radiation-hardened parts of the station. On the moon, you are well beyond the Earth's magnetic fields, but one of the awesome things is, and this is why making asteroids into spacecraft is such a tempting thing, if you get yourself under the soil, if you get yourself under the rock deep enough, just the rock alone will protect you from that radiation. So as we look to build habitats, both hopefully someday on the moon and on Mars as well, it's inside these cave systems that for the lowest cost we can build the safest dwellings. And heck, if the walls are already built for us, you're right, all we have to do is inflate our home. And there's other commercial agencies, I don't know if you guys are working on this, I know Bigelow's looking to build inflatable orbiting hotels. But inflatables is the new neat technology that's getting explored. What is your greatest hope for the future of these caves, John?
Yeah, the inflatables are a great point, and Bigelow has even shown some interest in the moon as well. So it's possible we could see these things. For me, I think these caves and exploring the moon, I mean, I think that's where you're going to have a permanent human base. It just makes sense. I mean, other models of settling on the surface and covering with soil yourself just doesn't make any sense because of the added infrastructure. But if you could drive down to the bottom of these caves, it just makes a lot of sense. You could imagine a solar array field that's spread out across the surface that's providing power during the day. You could hide out during the night and hide out during high solar radiation times, and then you could come out during the day and do your surface operations. So I think eventually we will have a scientific outpost on the moon. And I think that the caves are a very viable candidate for that outpost. I also think that eventually tourism will actually reach the surface of the moon at some point. If you look at tourism and the arc that's going on there into space, it's incredibly exciting, and I think it will reach the moon. If you look at Virgin Galactic, I think their latest number is somewhere upwards of 600 or 700 tickets sold to go to the edge of space, and those are going for between $200,000 and $250,000 per ticket.
Yeah.
And someone fairly recently bought a ticket to fly around the moon and come back. And this is, we don't know who has bought it, and apparently they paid something, started paying something like $150 million. But if they sell the second one, that mission will actually go. So I think it's just a matter of time before someone will pay to be the next Neil Armstrong or Buzz Aldrin to land on the moon and explore it and get that experience.
And to put some scale to that $150 million, that is significantly more than NASA's entire budget for education and communication of all its results. So I believe last year's budget was $120 million. This year's proposed budget was less than $100 million. So one human being spent more money to someday potentially orbit the moon than NASA has to communicate its results to the world and educate tomorrow's children to be explorers. It kind of makes my heart hurt, but it's kind of awesome all at the same time. So I'm facing this with mixed emotions, and I'm going to switch topics because it's less painful. Robert, you guys are actually getting ready to do a analog mission simulation, and the great thing about this is with the analog mission simulations, we can safely test everything out in some of the harshest environments on Earth and get the world engaged. Can you tell us all about your analog plan simulation?
Okay, so I think the best start is actually to explain to people what analog mission simulation means, because I have to admit that at the very first time I had a hard time to understand why people were using the term analog. So this means that we want to test drive all our technology as flight ready as possible. So if it's flight ready, then we take this kind of technology, for example, this rover. Or if it's almost flight ready, then of course we take the most advanced system that we have and bring it to a testing ground, which is, just describe it as it is. So we will start our testing in the Erzberg region in Austria, which is at it's an active iron mining site. So it really is a rough terrain, and it looks a whole lot like the surface of the moon, except that it's red, so it looks more like Mars. But just if you would take away the red color, then it would actually look a whole lot like the surface of the moon. And the most important thing is actually that you got a very small iron powder. I don't know the English term for this. There is a very good German term, but there's a very small iron powder, which is the remains of breaking apart all these stones over there. And it's very fine and very sharp, and it's a whole lot more, let's say, difficulty to deal with than normal sand that we have on Earth. So it's pretty close to the regolith that you have on the moon. It's not, of course, it's not a full regolith simulant, but it comes very close to this. And so we're having a region which is extremely large. So it means like driving around this 500 meters is totally no issue, except for the terrain in this case. So you just have to imagine an iron mining site. It's not like something where you can just walk in a flat area. It's just there's a whole lot of things of stones lying around, and so it's not easy for a rover to drive around there. And analog mission simulation in our case means that we want to try to simulate everything, every aspect of our mission as good as possible. So meaning we want to have a lander dropping off our rovers in the target area. These rovers will start the exploration of the area just like they would do on the moon. And these rovers will be remote controlled, not locally, but by two mission control centers. So one being in Innsbruck, another one being in German. So in Berlin, Germany. And the goal is actually to have all the controls simulated to be as if the crafts would be on the surface of the moon. So introducing a 3-second delay, communication outages, and all the technical issues that you can find. So there will be, of course, there will be people in place at this iron mining site, but they actually are not allowed to touch anything, and they are not allowed to help one of the rovers if it gets stuck, for example. So you really have to teleoperate everything and drive it remotely, and it's a very good way to test all the procedures and everything that you do in a mission control center, and of course see if the technology works in a realistic environment. And it's not just driving for 10 minutes, but it will be for 5 entire days. So, yeah, Carsten, do you want to add something?
Well, one of the challenges that most people are not noticing when they think about driving the rover on the moon is that actually you're so far away that it takes 1.5 seconds for light to arrive from Earth on the moon, and 1.5 seconds to get it back. And so the picture that you're actually seeing from the rover is 3 seconds, or at least 3 seconds late. And this causes quite some trouble when you don't have any artificial intelligence in it. And you want to try it wrong. And so this is another challenge that we are testing when you're doing another mission simulation. You're having a delay, you're having a low bandwidth, and you have a narrow field of view. And so the question that we also wanted to tackle back in the RRE was that how can you actually deal with the delay, with the low bandwidth, with the low quality, or not much higher quality than anything before, but with the quality of the video, and drive remotely in an unknown terrain.
So just to clarify these issues a little bit more, the problem that we're dealing with is nothing can travel faster than the speed of light because relativity, if you want to use internet terms. The issue is light goes at a finite speed. The moon is on average located 1.28 light seconds away from Earth. This means that if you fire a laser at the moon, which lots of people do, this was an episode of The Big Bang Theory, they couldn't have done that. Their laser wasn't big enough. But there's folks, for instance, at McDonald Observatory at the Lunar Laser Ranging Station that very precisely measure the distance to the moon, the changing distance to the moon. It's 1.28 light seconds from Earth to moon, another 1.28 light seconds to come off of one of those mirrors left from the Apollo astronauts, come back to the planet Earth. That puts you at about 3 seconds. So what you're dealing with is you see what happened 1.28 seconds ago, you respond to it, you send your command gets to the moon 1.28 seconds later, and you hope that nothing bad happened in between the two. Now, flying by wire with the moon actually is completely doable. The Soviet Union was able to go an amazing distance with their Lunokhod program. Lunokhod 2, which worked for just 4 months, was able to go 42 kilometers, which is 26 miles. So it essentially roved a marathon distance, quite literally. It did it in 4 months instead of 4 hours. But considering they drove the entire thing using that fly-by-wire with that built-in time delay, and they had to deal with the fact that you do have roughly every 14 days the sun goes down or comes back up, pick one. It's a lot to deal with. And both of your teams are working to deal with this in different ways, and the time delay is very difficult. A lot of cameras are required for this. What sorts of camera systems are your two sets of rovers dealing with? I'm going to go ahead and start with you on this one, Robert.
In this case, we've, as I mentioned earlier, when I've looked at the requirements of the GLXP, I found it quite interesting to see these high camera requirements. And so we started relatively early out to build our own camera system. And there's something that some people might know from a very funny YouTube video that we made. This was actually the very first proposed camera head that we built. Back in the video, there was a whole lot of electronics in there. It's gone now. I don't know where it is. It's probably disassembled and lying on some desk. But we're already about 5 iterations past by now. And so the next iteration of our camera head will be a very scientific, let's say, instrument, in a way that it allows us not just to fulfill, of course, the image requirements, be radiation hardened and deal with the thermal requirements, but also to understand the surface composition of the moon. And we want to test drive this camera at our analog mission simulation as well. So it's an interesting thing, because you're having a camera which can record in a quality where you hardly even can get this data down to Earth, because you're producing so much high quality data and you have a very limited downlink. So we always have to find a good balance behind it. And yeah, that's sorry, Carsten, do you want to say something about the camera?
No, I think you did well. I mean, one of the questions that you have to tackle is how much field of view do you actually want to have for driving, and how much field of view do you need for taking the absolutely stunning panoramas that are required by the requirements, and also do you want to have stereoscopic imaging, which we said yes, we want to, because this makes driving a little bit more easy if you can build a 3D map of your surrounding. So these are the questions that we have to tackled, and this is why we have a 2-lens configuration of wide-angle cameras and one telelens in the middle, which is more specifically for taking a closer look at stones or taking the panorama.
Yeah, and actually it sounds quite easy, like, hey, we're having a telelens on the moon and just zooming in on stuff, but actually there is no shop where you can buy such things. So you really have to develop all on its own and have to find ways to make it work and actually get it up there safely, because just building a camera system, you have to take into account all the loads, and I'm meaning the vibrations and everything, the entire shock of being launched into space. And yeah, it could shake up a lot of things inside such a, let's say, very advanced camera system. So you have to build things in a way that they actually survive all the way getting to the moon.
One of the things I've heard the current NASA director say several times is the most dangerous place for a spacecraft is the planet Earth. And this is because while you're on Earth, you're dealing with Earth's gravity, Earth's atmosphere, Earth's everything else, and it means you have not yet survived the horrible shaking and the horrible extra amount of acceleration which makes you feel like you're undergoing a lot more gravity that occurs during launch. Once you get to the moon, you're pretty safe. But getting there is indeed the challenge. Now, John, you guys are dealing with much more variable light conditions. Have you had to do anything special to take this into account with your camera system?
Yeah, the camera system, I'm glad you brought up Lunokhod as an example. It's a great example of just the amazing technology that they were able to implement back in the early 70s. I mean, they were beaming back images almost like a fax quality image. So it was really, really, really low quality images, and it was a TV signal that they were getting. And the other thing is that they only had one camera. So it's kind of like trying to navigate the world with one eye closed. You don't have that depth of field, and it actually got them into trouble. I mean, that's why they drove into a crater at one point, and they got some dust on their radiator, which ended up being a mission critical event for the lifetime of their vehicle. One big advancement that has happened since then is stereo cameras. So you can use two cameras, combine them, and you get that depth of field back, and then you can navigate and determine that there's an obstacle in front of you, or see a slope, or see a crater. So that's what our system will use, and it will be very much like a joystick system. So we will account for the delay. We've been doing testing with that. We've shown that operators can work with that delay, and it works just fine. The rover will have a low level of autonomy to make sure that it doesn't get in trouble itself. So if it receives a command to keep driving, and it just keeps driving, and we don't get another signal from it, if it gets on a slope that's too big or in a position that's awkward, it'll automatically stop and just wait for the next command. But imaging the pit is an extra challenge unto itself, because there's a very high contrast that's inside the pit. A lot of the floor may not be illuminated at different times. So we land at 45 degrees north, which means that the sun is never directly overhead. It's actually about 45 degrees up on the horizon. So you're always going to have those longer shadows, and it's possible that the bottom of the pit may not be illuminated. So we're looking into systems that have a very high dynamic range, so that you can pick up some of those features down in the pit, and even looking at things like an HDR type image, so that we can pick up those details. So we anticipate cameras on the rovers, stereo cameras that'll drive the rover. We also have a stereo pair that's also on our lander as we land down towards the surface. So and then also another camera very, very, very high up when we're orbiting the moon. We use the moon orbiting camera to determine where the lander is relative to the moon. So it's a little bit, we call it map registration, but it's a little bit like if you're out hiking and you see a mountain, or you see a stream, or you see a road, and you're like, well, I'm about here relative to these features that I can see. The lander is doing the same thing as it's coming down towards the surface. It says, oh, there's a crater I recognize, there's another one, and oh, well, the relative size of that tells me how high I am, and tells me how far away from my landing site that the robot is. So as it's coming in, we're using that camera to determine the destination. When we get close to the surface, we use a stereo pair to scan the surface, and it gives you that depth, so you're looking for slopes, looking for rocks, looking for any kind of hazards that could interfere with a safe landing. And we also use a laser scanner that's going to be scanning the surface of the moon as we fly in. That gives us another level of detail to look for the rocks and slopes and anything that could be a problem. And the laser scanners works a little bit like the laser that you get from Home Depot, where you stick it up next to the wall and you press a button and it gives you a measurement of your room, except this one shoots a line of those lasers out all at once. And then if you take that line of lasers, you're getting measurements back from every one of them, and then you move that line of lasers, you could actually reconstruct a 3D image of what's going on. So the lander will actually fly over the top of the pit as it's coming down towards the landing. We'll be looking down with the lasers, we'll be looking down with the cameras, and with that we'll be able to create a 3D model of the pit as we fly over it. There's a lot of really cool imagery and a lot of really cool things that we'll see out of this very first mission.
And this particular laser technology actually is a really awesome one that has been getting developed in a lot of different ways. It was initially getting used as what's called LiDAR, where you use lunar ranging from space down towards a surface to measure surface details by seeing how long it takes the light to reflect back to the spacecraft. Depending on how the light gets scattered, you can also tell things about the texture of the surface. We've used LiDAR on Mars, on Earth, on the Moon in the past, but what you're looking at is significantly higher resolution than has been done. what's also kind of awesome about this is as the technology is getting advanced more and more for spacecraft, we're getting some really awesome uses of it here on Earth. It's not just the folks going to Home Depot and getting these lasers to range across the room. They're also working to develop new forms of canes for the blind, where instead of moving a physical cane, you have an earplug and a laser, and it does that same distance measuring and uses pitch of sound to indicate where obstacles are located. So this is a really great technology that isn't just for the moon. It's also revolutionizing how we do things here on Earth. Now,
That's absolutely right. And another one is we're actually using these lasers to drive autonomous cars here on Earth.
Yeah.
So Carnegie Mellon won the DARPA Grand Challenge, which was autonomously driving robots, and it was covered with lasers that are scanning the terrain. And now they're integrating these into vehicles, and they'll be available production autonomous cars by 2020, and they'll have these same lasers in them.
And if any of you have had kids or are yourself a teenager who's participated in any of the robotic challenges, there's some that are built off of the Roomba, there's some that are built off of the Lego model, there's a variety of different models. There's actually a Moonbots challenge that's hosted by the Google Lunar X Prize that I'd encourage you to go. They have some fabulous videos on YouTube, and many of these robots are also employing lasers. It's really a neat day when we're training middle school and high school kids to build autonomous rovers using lasers. But I think the real question that everyone has is when. Where's my jetpack has been replaced with when are we going back to the moon? So, Robert, when are you guys hoping for at this point?
We are aiming for the third quarter of 2015. So I think it's probably the same date that all of the GLXP teams are heading for, because 2015 is really the last time that you can do it, of course, by the rules of the competition. And I think also it's about time, because the initial GLXP was set out in 2007. And yeah, I think it's about time to get back to the moon.
John, what was your team looking at? Still there, John? I think we may have lost John's video. Hopefully he'll be coming back. Google is now acting up in fascinating ways. Okay. So Robert, it sounds like many of the different teams... Okay, now we have John back. Sorry, John, your video paused for a moment. Can you tell us about when you're planning to land?
Yeah, so sorry about the delay there. So we land in 2015, October 2015.
Oh, he completely dropped off. Okay, I'm going to go back to you, Robert, and hope that John is able to rejoin us. So I heard that several of you are going to be sharing launch vehicles. Is your mission going to be one of the missions that's sharing a launch vehicle with other teams?
No, we're not so into sharing launch vehicles, but as I said, as I pointed out, for us the most important thing is technologies, and one thing that we actually do share is the technology that we've developed. So to give a very exact example, is for example that the camera that we've developed is that we will license this technology to one of the GLXP teams.
Okay.
And I think this is a pretty exciting fact, because it shows that the technology that you develop has an actual value to future missions. And of course there are some other third parties outside of the GLXP which have also requested access to some of the parts of the things that we've built, and I think the same will be true for a lot of other GLXP teams. So, and I think this already in some way or the other actually made the GLXP be worth it.
So with the Google Lunar X Prize, there's these 18 teams still going and active. There are missions that are sharing technology that are hoped. There's missions that are sharing launch vehicles. Astrobotic is one that's sharing launch vehicles. You're slowly working on building a community that both works together and competes against one another, and kind of what I remember is the heyday of Boeing and Martin Marietta and Lockheed and all of these different companies that were competing for NASA contracts but building stuff for one another. where do you see as the future? And while you think of an answer, I'm going to remind our audience who hasn't been asking a lot of questions, probably because I didn't remind you. You can ask questions anytime you want, either out on the events page or on the YouTube page. The Q&A app, for reasons beyond our control, did not work with this Hangout. We assume that Google's working on that in the background. And Google and Google Lunar X Prize are not organized by the same people, so this wasn't our fault. So go ahead, post a comment on YouTube or on the events page, and I'll bring it to our audience. So Robert, I'll start with you. Where do you see space in 10 years?
I think it's hard to estimate being in 10 years or not, but let's say it differently. My personal goal for space in the future is actually to, and this is what I'm aiming at with PTS, is actually establishing a layer, a foundation of technology. So being able to, I don't know, for example, today, if a company is thinking about sending a robot to the moon to mine the surface area of the moon, so they figured out something, they had an interesting business idea, and they say, hey, we need this rare mineral off the surface of the moon, and I want to get it. So as of today, they would have to develop everything on their own. They would have it's like rebuilding the wheel. So not rebuilding, reinventing the wheel. So, and what we want to be able, or what we want to contribute to, is to open up a portfolio of technology and, of course, services. Not just the technology, but actual services that somebody can just buy in and do things on the moon a whole lot cheaper than if he would do it everything on his own again. Because you have to understand, currently missions to the moon, they cost into like in the multiple hundreds of millions. And this is actually a magnitude that a normal private company can't pay. So a company, for example, they could actually say, okay, we are giving out like 10 to 20 million US dollars or euros, but 300 million is definitely way out of the league. So it's actually not so interesting. But if you get it down to a level where people can actually do something in space and on the surface of the moon, it's like with CubeSats, then actually I think, and that is my hope, that we will see something like the internet revolution for space.
That would be fabulous. And what I recently saw come across my desk is NASA is actually currently competing. It may be the National Science Foundation. NASA or the National Science Foundation is currently competing a grant to build CubeSats and launch CubeSats. So it's now become something that your everyday professor at a small university can apply for federal funding to launch their own small mission to space. The future belongs to everyone, thanks to reduced technology costs. Before I go to questions, Robert, where do you see things going?
Didn't you just...
sorry, wrong name. John, sorry.
Oh, thanks. Space is an incredibly exciting place, and it's not just because we just think it's exciting because it's space. That's cool in itself, but it's also there's huge sea changes that are happening that are disrupting the entire thing. One of the biggest is that the cost to get to space is coming down dramatically. So what used to cost $10,000 per pound, think Shuttle and Atlas and Delta, like a traditional launch vehicles, this year SpaceX and Elon Musk will launch what's called a Falcon Heavy launch vehicle, which for the very first time will reach the $1,000 per pound barrier. So it's 10 times cheaper than we've ever imagined to fly into space, and that will continue to fall. So just in that 10x reduction in cost, we're seeing a huge resurgence in what a lot of people are calling new space, a lot of new technologies, a lot of small prototypes like the CubeSats that Robert was talking about. We're seeing startups now that are able to compete and do the same things that governments or billion-dollar companies were able to do previously. We're extending that same idea to the moon. So our first mission sells payload by the mass. So you can buy a piece of that mission starting at $500,000 per pound. And recently there was a Forbes article that kind of described how you would use this. There's a NASA Ames payload. They want to germinate seeds for the very first time on the surface of the moon. Normally that payload would have to convince NASA, their local space agency, that they have the coolest science in the room. And then they'd have to convince NASA to spend $300 million to get that science to go. Using our service, they can launch and land on the surface of the moon and do their science for less than $2 million.
That's
so for
awesome.
them every other organization from around the world, this is a game changer, and our model is extending this big cost savings that we're seeing in the future of space.
And to give you a sense, $2 million sounds like a huge and vast amount of money until you start realizing that small business owners, university professors, all of that, they have to pay electricity, building fees, medical insurance. And $2 million is really enough salary for 4 people for 4 years. Once you start adding in overhead building costs, accounting fees, all of that sort of stuff. So small business, 4 people, 4 years, or let's go land on the moon.
Yeah, it's
really
incredibly
awesome.
exciting, and people from around the world are capturing this and understanding this and getting really jazzed about it. And other X Prize teams are also able to jump on board with us too. It's an open door to anyone else. We expect to make some announcements soon relating to that. But it's an incredibly exciting time to be in space, and it's only going to get better from here.
So we've hit noon, but can you guys hang around for like 5 or 10 more minutes to answer some questions from the audience?
Sure.
Okay, so this is, I think, my favorite, from Nancy Graziano. She asks, when each of you were growing up, did you want to be an astronaut and actually go to the moon? Would you be interested in going today, or are you satisfied with sending your rovers there? And Karsten, I'm going to ask you because you're the youngest. Start with you.
Well, I didn't actually dream about it. I mean, personally, I think that going to the moon is a bit boring. But if I could go to the Mars, I would actually prefer go there because it has an atmosphere, and I don't feel like I'm being in an X-ray all the day. So I would probably live longer there. So until we solve that problem, I think I would prefer being an astronaut on the Mars. But I think that the most important thing that that could bring technology forward is that we beat the rocket equation, and for this we could use 3D printing technology.
Yeah.
And while I enjoy thinking about the idea that we are being lunar cavemen, I would rather have a 3D printed home that like ESA was exploring in the last year or something. And so maybe I would feel at home in such a base.
Yeah, I kind of see a future where we blow up the initial home, sort of like you sometimes stick a trailer on the property while you build the actual house. So blow up your temporary home, not like explode, but blow up like a balloon, and then 3D print the big thing. Yeah, the future is quite awesome, and you bring up a really good point. I'll never forget the look on Carrie Bean's face. She's now I think she's one of the operators of Curiosity. At the time, she'd been working on Mars Phoenix, just finished her PhD, at the time was a grad student. Jim Green at NASA made an announcement at the Lunar Planetary Science Conference just off the cuff that the astronauts who go to the moon will not be allowed to go to Mars due to the radiation dosing problems, so you need to pick one. And the look of, I can't go to both. This is a true reality that we're facing until we can completely solve the radiation problems. So Alex, I'm sorry if I mispronounced your last name, Alex. Alex Gyongtoy asks, both teams are on the very frontier to reach certain Google Lunar X Prize goals. Which partners outside your core team have proven to be the most important to get you there so far? Not necessarily regarding monetary contributions, but more in terms of knowledge, service, research, and commitments. Who are your go-to men and women when you need things beyond what your team can create for yourselves? John, I'm going to hand this one to you first and then go over to you, Robert.
Great. Our go-to partner is Carnegie Mellon University. So they're less than a mile from where we are, based here in Pittsburgh. They have the world's #1 computer science program, and also their top 10 engineering, and usually #1 or #2 in robotics in the world. So because this is a space robotics problem, it's all the right people to have under one roof that's right next door. They typically operate a class that can involve and do related research projects associated with. So we have people from freshmen all the way through PhD students who get a piece of the project and can explore it and be a part of it in some way. It also turns out to be a great testing ground to eventually become a full-time Astrobotic employee. So I definitely put Carnegie Mellon on the top of our list of great partners.
That sounds great. Robert, who do you turn to?
Okay, what I have to say is that what we realize is that actually a whole lot of people step forward to support us in what we do. So it's not just like that we're reaching out to organizations and ask them for help, but it's actually that the entire space industry is really interested to get things going. So just from the knowledge point of view, for example, a partner that we've working with this year very prominently is the ÖWF, which is the Austrian Space Forum, as well as the TU Wien Space Team, which help us, for example, it's a team of rocket scientists at the TU Vienna, which helps us with the lander development, the Earth-based lander development for this year. And then, of course, the DLR, which is I think, German Space Center would be the best translation. But besides this, we have about 50 industrial partners, so companies will help us with certain types of technologies, and I think this is pretty interesting. So there are companies stepping up and saying, not just you can use this integrated circuit, but also we help you with the knowledge behind this integrated circuit and getting it certified or working on the moon.
Okay, that's all great. And I have one final question. Where did you hear about the Google Lunar X Prize, and how long did it take you to go from to I'm going to do that? John?
We first heard rumors of it before it was announced. We said yes at the rumor level. So the moment we saw it go out, we were right in and threw our hat right in on day one.
That sounds great. Robert?
Yeah, for us it's a little bit, I don't know, a little bit funny in a way that I've got an email from a very good friend, and he just sent me this link and said, hey, look at this. And it was about the end of 2008, and it was like less than 3 days to go before the final registration deadline was closing. And that is probably the reason why he found the competition on the internet. And maybe he read an article that the competition is closing in, and he sent it to me, and I had like 3 days to decide if I want to file in this registration. And it was like, I don't know, it was like crazy. I was just printing out all the information, reading through it, and thinking about, would it be possible? Does it make sense? Is it interesting? And yeah, we've applied for it, and I don't know, it was probably the best decision of my life so far.
This is all a great adventure, and thank you for sharing your adventure with our audience. Where can folks learn more about your missions? Robert?
Yeah, just simply use the search engine that you like and type in hell yeah, it's rocket science. Because
okay, that might lend some people to things they don't want. Is there another way to find it?
Yeah, just type ptscientist.com into your browser or whatever you like. So we're pretty easy to find. Just look for part-time scientist, hell yeah, it's rocket science, or ptscientist.com.
Okay, John, how do they find you online?
So we're right on astrobotic.com, and I might also point out that we now have an article that's on space, just launched on space.com today.
So thank you for joining us. I'm sure we'll have you back again in the future. This is part, for those of you who don't know what you tuned into, this is part of a new series that we're putting together. Google Lunar X Prize wants to help everyone understand how we're getting to the moon, and how these 18 teams that are still part of the Google Lunar X Prize are defining the technologies, defining the protocols, and everything else that we're going to need for our return journey. We are going to be alternating time zones, so stay tuned. All of this I should be posting later today on the Google Lunar X Prize Google Plus page. Everything will be mirrored on CosmoQuest, where I encourage you to come and help us map the moon so these folks know where it's safe to land and where it's awesome to explore. Thank you for joining us. We will be at a different time with different people next week. All of this was on Google Plus. John, Robert, Karsten, I can't thank you enough for spending the last hour with us and with our audience. I'm sorry if we didn't get to everyone's questions. Leave the questions on YouTube and on Google Plus, and I will forward them to the teams, and hopefully you'll hear back your answers. So thank you, everyone. This has been great.
Thank you, too.
Bye.
Thank you, Pamela. access to that. We don't have the budget for that. It's incredibly expensive, and you eventually need a presidential approval and a lot of schedule to support it. So we're not going that route to survive the night. Our approach is to find electronics and find technology that can just survive that cold. So the very first thing that we've found so far is a battery that you can put down in liquid nitrogen temperatures and bring back up the next day, and it still has the same charge as it did before it went down. So we found a battery that could survive that night. So it's a really big step, and all the tests that we've seen so far are proving very successful that the electronics can in fact come back the next day. So we're going after the distance to explore the pit, and we're going after surviving the night so that we can extend our stay on the moon.
And just to help provide our audience who may not be as familiar with batteries dying in the cold and radioisotopes, radioisotope is a fancy scientific word for a bunch of atoms that are not entirely stable and go through a radioactive decay process. So you have things like uranium, cesium, plutonium. There's a whole variety of different choices that you have. Some of them get used in medical research. Some of them get used to treat cancer, and they actually will put some of these into the human body. And when they decay, they release, among other things, heat. And with a spacecraft, that heat can be used to provide energy and to just keep the spacecraft warm. This is how the Cassini mission is working. The New Horizons mission, which is the fastest thing in the solar system, that's, well, fastest man-made thing off the planet in the solar system, is on its way to Pluto. But we're out, for the most part, in the United States, of the materials that we'd normally use, so even NASA folks are having trouble getting it. Batteries in general, just for a whole lot of chemical reasons, you get them cold, they stop working. This is why when you're hiking, you often have a headlamp with a battery pack that's up close to your body along with your water bottle, so your batteries don't freeze.
A place called Locus Mortis on the surface of the moon. So this is, it translates to Lake of Death, which sounds dramatic, but the reason that we go there is there's a very unique feature that only exists there on the moon. It's called a skylight. It's 100 meters across and 100 meters deep, and if you can get to the bottom of it, it's an entryway to a lunar cave network underneath the surface. They've found upwards of 150 of these on the surface, but the one that we like at Locus Mortis has a ramp that you can actually get down into and potentially get down and explore these pits. So our first mission goes there. What we do as a business and as a company is we sell payload. So we're like a UPS or FedEx to the moon, so we'll be bringing many other payloads from around the world with us on this first adventure. We'll also have a rover on board that will drive 500 meters, and it's very likely that we'll have other X Prize teams along board with us. So it will be an incredibly exciting adventure, and that's just a quick snapshot of where we are.
So Robert, would you like to introduce us to part-time scientists?
Okay, hello everyone. I'm Robert from the Part-Time Scientist, and as a little bit like an elevator pitch, what could be said about our team is that we're a private team of scientists and engineers, so working part-time on this mission to the moon, so really are technology enthusiasts. And our goal is actually to establish a foundation of technology to support ongoing private exploration of the moon. Because for us, I think it's not the focus is not on having one mission going to the moon or like being a delivery service to the moon, but actually establishing a layer of technology that makes it possible for everyone to access resources in space a whole lot easier. So if you think about space exploration, then everything sounds like things sound like they're settled. So it's like, oh yeah, we have communications, but in reality, things are a little bit more complicated. And our goal is to offer some solutions which hopefully solve currently existing problems a little bit better. So it was a little bit overly complex definition of what we do, sorry. So yeah, and together here with me is Carsten from our electronics team. And yeah, maybe Carsten, do you want to say something?
Hi, yeah, I'm Carsten from the electronics team, and so I'm concerned with getting the electronics to the moon. And one of the things that I noticed is that especially in the space industry, that electronics are very expensive, and so we want to see what technology, and especially they are very outdated. So if we take a look at Curiosity, it is a processor that is as old, that you wouldn't even put it on a current smartphone, But so we want to check what current technology we want to use and see what we can do with it on the moon. Hopefully, drive around and take pictures. That would be great.
Yeah. So to say it as I said already, our team is all about technology and finding new ways to put new technology to solve existing problems that we have in space. So yeah, of course, our goal is also to send multiple missions to the moon, but the very first one is just as a technology demonstration. So we try to cramp up as much as interesting pieces of scientific experiments or new technologies into this mission and try to see how it performs and what value it adds to future missions.
Now, one of the great things about the Google Lunar X Prize is, while the primary goal is to go successfully land on the moon, successfully go 500 meters, successfully send back video, there are a variety of other milestone and additional challenges that range from technology challenges to Apollo heritage challenges, and each of your teams is striving toward different of these additional goals. John, can you tell me which of these different goals your team is working toward?
Sure. Our team's going after the distance prize.
Hello, everyone, and welcome to the first Google Lunar X Prize Team Hangout. My name is Dr. Pamela Gay. I am the principal investigator for CosmoQuest, a project that is very Earth-based, but we're down here mapping the moon in hopes that someday people will go and explore it, and these are some of the people that are working to make that exploration possible. Today I have with me John Thornton, who is the Chief Executive Officer over at Astrobotic, which sadly sometimes gets written as Astrobiotic, which I'm sure must be an interesting trial for him, but it's Astrobotic, astronomy, robotic combined together. I also have with me PhD student and electronics guy Karsten Becker, and the CEO, team lead of part-time scientists, Robert Bohm. Today we are going to have each of these two teams overview what their mission plan is at this point. They are two of the 18 teams still actively pursuing the Google Lunar X Prize. The Google Lunar X Prize is put out to help encourage people to build rovers or some other form of robotic critter that will go to the moon, go a distance of 500 meters, and then send back video to Earth. And there aren't any restrictions on how you go those 500 meters. In my head, I've always envisioned like a little Sony robot kind of doing the boogie as it goes the 500 meters, because that would be great for YouTube. But they have much more scientifically planned ideas of how to do this, and they're going to introduce us to their plans. And John, I'm going to go ahead and start with you because you appear furthest to the left on my screen.
Awesome. Thanks, Pamela. Thanks for having me today. It's really great to talk about what we're up to. So our first mission wins the X Prize and flies to, which is driving 5 kilometers. So the way that we'll do that when we land next to this pit is we'll land next to the pit, we'll drive up to the rim, and we'll explore that pit and drive all the way around it and look into it for the very first time from the surface. We've only ever seen these pits from space. So it will be incredibly exciting to actually see these up close and see how these things were formed. No one knows how they were formed, which is incredibly exciting. And it's also really exciting to scout out the location, because these pits, especially this one destination, has a ramp on it, which means that it's a potential site for future humans to habitate. So if you think about it, if you're underground on the surface of the moon, it's the same reason that you would settle in a cave here on Earth first. It protects you from the elements. If you're underground, you're protected from the solar radiation, which currently limits the careers of astronauts, because once you hit your dosage rate, you have to come home. But if you're underground on the moon, you're protected from that. It also can protect you from micrometeorites. The moon doesn't have an atmosphere like we do here on Earth, and those can come flying in and become a problem for people. And if you're underground, you're also protected from the thermal extremes that exist on the surface. It gets up to 120 degrees Celsius, which is about 250 Fahrenheit, down to liquid nitrogen cold, which is about a minus 180 degrees Celsius. But so if you're underground, you're protected from all of this. So our first mission is going to spend a lot of time exploring that pit, and that's likely how we'll get up to about 5 kilometers of distance. The second prize that we're going to be going after is the surviving the night. So in order to survive the night, you have to operate after a cryogenic cold period of 14 Earth days. So it's minus 180 degrees Celsius for 14 days. It's incredibly cold. A lot of times governments solve this problem by using a radioisotope. So it's essentially a hot material that's decaying slowly over time, and you're able to use that heat to keep your spacecraft or rover warm over time. Because we're a commercial entity, we don't have